that in the last class we have read about this resource request algorithm, and this problem we have solved. In your problem, the max will be given, allocation will be given, from which you will compute the need matrix, that is the max minus allocation. With the available resources, we will try to fulfill the need of the processes. If you could able to fulfill the need of all the processes, then we will say it is in safe state. Otherwise, we say it is not in safe state. If you provide the need for a particular okay, so from which we compute that whether it is in safe state or not. Now, the second part of this problem is that if a process, suppose the process P1, showing the internet is unstable. Okay. Suppose the process P1 makes a request of 102. So this is my previous state. The P1 is making additional request of 102, whether it will be granted or not. We'll assume that 102 is granted to it. So if 102 will be granted for P1, so we'll add 102 to this allocation. So this becomes what? 302. This 102 will be added to this P1 so that it will become 302. From where this 102 will get? We'll get it from the available only. So available minus request. So 332 minus 102, it becomes 230. I hope you are understanding. P1 makes a request of 102. We take 102 from available, so it becomes 230. That 102 we give it to P1. So this becomes 302. Is it understood up to this? Is it understood or not? The P1 makes a request of 102. We take from the available, so it becomes 230. I don't know, today it's disconnecting multiple times. Let us see. Okay, so we are subtracting 102 from here and adding to P1. So this is my new matrix that is given. Now from this I can find out the need. Need is nothing but the max minus allocation. For other processes it will be same. Only for P1 it changes 322 minus 302. This is 020. So what we have done, we have assumed that we are allocating the resources to the P1. Now by allocating these resources, we have computed the need matrix, and again we'll run the same algorithm to check whether it is in safe state or not. Whether it is in safe state or not. So we are available with 230. Can we give 230 to first process P0? No. Can 230 be given to second process? 230. You can give it to the second one. So we can give it to P1. So once the P1 it will be given, we can add the available of P1 to. So this is 230. This is need is 020. Right? I can give it to P1. If it will be given to P1, then P1's allocation will be added. The P1 allocation is 302. So we'll add it over here. So that becomes 532. Now with this 532, can I satisfy any other process? Yes, we can satisfy this one, P3. So we'll again add the allocation of P3, that is 211. We'll add this 211, correct? So it becomes 3, 4, 7. Now with this 7, 4, 3, can we satisfy any other? Yes, we can satisfy P0. So P0 can be satisfied, and we'll add for P0, 0, 1, 0, we'll add it over here. we'll add this 0, 1, 0, correct? And we'll get the 7, 4, 3, 7, 5, 3. And again, we'll go for 7, 5, 3 can be given to anyone. Yes, I can give it to this one, that is P2. So P2 allocation will be added, that is 302, right? Hello, are you on, do you understand or not? So with this 755, I can satisfy this one, right? P4 can be satisfied, and I can give this 002. 002 will be returned. Correct? So, so I mean to say that by if I go on allocating this 102, even if I allocate this 102, it will not lead to unsafe state. Correct? So this I get a safe sequence over here. Okay. Is that understood? Is the problem understood or not? So question will come, try to understand. Is the screen visible?
Yes, sir.
Okay. In the problem,
Sir, can you explain again?
just like. So in your problem, it will be given. Suppose this scenario is given. This is given. You have been said, you have been asked to check whether it is in safe state or not. So that you can check, because in the previous class we have done max minus allocation will do and go on checking. In the second part, it will be given that if a particular process, suppose P1 request a particular resource, whether it will be granted or not. So what will do? This value will subtract from this available, so that you will get the new available. Then that value will add to this P1, whatever is given over here. You will add it to that P1, so that you will get new P1 value. Now simply run that previous algorithm. You will have new need over here because mass minus allocation is changed. Correct? So you take this value 230 and check that to whom we can give. You can say, you can check over here 230 can be given to P1. If it will be given to P1, P1 will be added, P1 allocation will be added. So that becomes 532. Now to 532, so we got the first value as P1. Right? So this, with this 532, whom I can satisfy? 532, I can give it to this one, P3. Correct? So P3 is, P3, if it will be given, its allocation 211 will be added. So it becomes 743. So we have allocated to P3. We have allocated to P3. Correct? So with this 743, we can allocate P0. So we give it to P0. So once we give it to P0, P0 allocation 010 will be added. So it becomes 753. With this 753, I can allocate P2. I can allocate P2. So once P2 will be allocated, P2 allocation 302 will be added over here. So it becomes 10, sorry, not 7. This becomes 10, 5 and 5. With this 10, 5, 5, I can allocate the P4, and for P4 it is 002. So it will be 10, 5 and 7. So I got all my resources and all processes are satisfied. So I'll say this is in, if I go on allocating this 102, still it will be in safe state. Still it is in safe state. But while allocating, if I found any one of these is not satisfied, then I will say it is in unsafe state. You can check it by with this problem. You take P4 is requesting 330. If P4 is requesting 330, I will delete from here. I will subtract from here 330. So it will become 002 over here. So this will be allocated to P4. To P4, if I allocate 330, so this need will also change. And you will again run the algorithm, and you will see that some processes cannot to some of the process, the demand cannot be fulfilled. That means it is not in safe state. So we will not grant the request. Is that understood? Is it understood or any doubt? If you have doubt, hello? Hello, I could not hear. Hello? Type on the chat box. Is it understood or not? Or I will explain for these values. Suppose P4 is requesting 330. Can you do of your own or not? This 330 you will subtract from here. This 330. You will get what? You will get 0, 0, 2. So now your new value will be 0, 0, 2. The new value will be 0, 0, 2. And this we have to allocate to P4. So P4 will become how much? P4 allocation with 330, 330, that means 332. So now this will also change. 4 minus 3 is 1. 3 minus 3 is 0. And 3 minus 2 is 1. Now with this 0, 0, 2, to whom we can satisfy? Tell me, to whom we can satisfy with this 0, 0, 2? Can you satisfy any one of these? 0, 0, 2.
No.
So therefore, it is an unsafe state. That means P4 should not be granted. Therefore, P4 should not be granted. Correct? I think it is understood now. So that is being explained over here. So one of the limitation of the Banker's algorithm is that it takes the high complexities, almost order of n into n into m. If n is the number of processes and m is the number of resources, so almost n into m or n cube amount of time it takes. And there is no guarantee of a user can satisfy within a definite period of time. There is no guarantee. But however, Banker's algorithm is very much useful in many of the cases. Now what we have read about the deadlock prevention. We have read about the deadlock avoidance. Now the third one is deadlock detection. If a deadlock occur, then how to detect the deadlock, detecting the deadlock. And once it is detected, how to recover from the deadlock. Correct? So to detect a deadlock, so if a system doesn't use either a deadlock prevention or deadlock avoidance algorithm, then system get into deadlock. So in this case, we have to detect the deadlock by using some detection algorithm to know whether deadlock has occurred or not. If deadlock has occurred, then which processes are in the deadlock? And then we'll try to recover from the deadlock. So we'll read now deadlock detection and deadlock recovery. So if they are single instance resource type, that means every resource has only single instance, then we use a graph called wait for graph. We use a graph called wait for graph to detect whether deadlock has occurred or not. Try to understand. The resource allocation graph is used again for deadlock, where you have used the resource allocation graph content cycle, then it is a If it has single instances, then it is a deadlock. Similarly, there is a graph called wait for graph, which is used for detecting the deadlock. The wait for graph is almost same as the resource allocation graph. The wait for graph is almost same as the resource allocation graph, right? So in this wait for graph, we have some processes and resources. We have some processes P1, P2, P3, P4, P4. We have some processes and some resources are over here. There is this we can think this is a resource allocation graph. Resource allocation graph you already know. I have already explained you the resource allocation graph. Processes and resources will become the vertices, and there are two different types of edges. Just a second. Okay, so hello.
Yes, sir.
So this is the resource allocation graph. What we'll do over here, very simple. If there is an edge from process to resource and resource to process, just to check over here, process to resource and resource to process, then what we'll do, we'll remove this resource and we'll make a direct edge from process to process. Is it understood what I'm saying? If there is an edge from a process to a resource and resource to a process, so I'll remove the resource and I'll put process to process. Correct? So you check over here, P1 to R1, R1 to P2. So I'll put an edge from P1 to P2. Similarly, P2 to R3, R3 to P5. So I can put an edge from P2 to P5. So I put it over here, P2 to P5 by removing this R3. So you'll see that P2 to R4, R4 to P3. So I can put a edge from P2 to P3. See over here, P2 to P3. Exactly in the same way, if you look over here, P4 to R2 and R2 to P1, P4 to R2 and R2 to P1. So I can put P4 to P1. See over here, P4 to P1. P2 to R5, R5 to P4. So P2 to P4. So I'll have edge from P2 to P4. Correct? P3 to R5, R5 to P4. So I can have a edge from P3 to P4. Correct? So we have drawn all these edges, removing all the resources. Now these resources are not required. So this is your wait for graph. The wait for graph doesn't have any resources as vertices. The wait for graph doesn't contain any resources as vertices. So I'll get this one. And from here, if the wait for graph if the wait for graph contains a cycle, then it is in deadlock. But do remember, if everyone has single instance time. So I'll say it is in deadlock. The wait for graph is in deadlock. And the processes which are involved in this wait for graph, those are a part of the deadlock. Is it understood what I'm saying? So you can convert the resource allocation graph to the corresponding wait for graph by removing the resources. If there is an edge from process to a resource and resource to a process. If there is an edge from Pi to RQ and RQ to PJ, then we'll put it Pi to PJ. So that we'll get another graph is called the wait for graph. We'll get it wait for graph. And if the wait for graph contains a cycle, then it is in deadlock. The processes in that wait for graph are involved in the deadlock. And this requires n square operation because we are just traversing a graph. Graph traversal will take n square operation actually over here. But this is only for single instance resource type. Is it understood or any doubt? So that we'll go for multiple instance resource type. Is it understood? Is it understood? This is very simple. Is it understood or not? Hello?
Yes, sir.
Okay, okay. So now we'll go for several instance resource. This is for single instance resource type. But for several instance resource type, we'll use similar or similar algorithm of the bankers. We have taken a data structure available over there. Here also we'll take available. Here also we'll take allocation and request. These are same as of bankers algorithm. Available means it is a vector of length m indicating the number of available resources. Allocation n cross m matrix define the number of resources of each type currently allocated. Allocation. The request is a process. Each n cross m matrix indicates the current request of each process. So directly we are going to the detection algorithm. So see over here what we'll do. Work and finish be the vectors of length m and n respectively. So what will take the available will take work is equal to available. So actually what we have, why we have done over here, so that we do not want to change this available, the original one. Whatever changes we'll do it in the work. So that means it is a temporary changes, just to check. So initially we'll make all them as false. For I is equal to 1, we'll make them false. If it is for I is equal to 1 to n, if allocation of I is not equals to 0, then we'll make it false. If allocation is 0, that means nothing is allocated, it is true. Right? So we'll find some process is having false, that means something is allocated and its request is less than work. Right? If such I doesn't exist, we'll go to step 4. Otherwise, what will happen? Will work is equal to work plus allocation and finish of I equals to true. So initially what we'll do, we'll take a matrix. All these are false. All are false. Correct? This is the same as the previous algorithm, the bankers algorithm that we have discussed. So these are false. So if it is 0 allocation, that will be true. So now it is false. So the first one will choose whose value is false and the request is less than available. Request is less than available. Work is actually available. Request is less than available. So in that algorithm, we write over here need. Now you are writing request is less than available. So what we will do? We'll allocate it. So available equals to available plus allocation. So we will allocate it and we'll make it true. We'll make it true. Right? So similarly, I'll go on allocating one process and we'll make it true. Correct? So if finish of I equals to false for some I, but still I found that some processes are false. Some processes are false. So finish of I false for some n, for some I, then it is in deadlock, and these processes are involved in deadlock. And this also requires m into n square operation. You can see this is the same as the previous algorithm that you have discussed, almost same. Here only, see, this is the algorithm. This is the algorithm that we have had. We take work and finish, work is equal to available, false. So we do the same thing. Only thing is that we just set the value over here to true. It checks, but here it checks. It checks this. If allocation is not equals to 0, we make it true. And it just checks that whether it is in deadlock or not. If it is in deadlock, those processes whose value are false are involved in deadlock. So detection algorithm is almost same as the safety algorithm of the that we have read in the bankers. I hope it is understood. Detection algorithm, this is for what? This is for multiple instance resource type. Wait for graph is for single instance resource type. So detection algorithm is same as safety algorithm. The only difference is that whose value will be false. If the some value will be false, then it is in deadlock. And for those it is false, they are involved in deadlock. Is that clear or not? Is it understood? So the same algorithm will run over here. This is an example. We found that these are all true, but if something is false, then we say it is then it is in deadlock. Is that clear? Is it understood or not? Hello. So now what you'll do, this example you will try to execute of your own, run of your own. Same algorithm, the detection algorithm is banker's algorithm, will run of your own. If you do not understood, the next class again you ask. So now thing is that we have read about allocation, we have read about we have read about the prevention, we read about the avoidance, deadlock detection. Now we'll go for deadlock recovery. For deadlock recovery, what we'll do, over here, one is by process termination. We'll terminate because some processes are involved in the deadlock. We'll abort all the processes. Sometimes your system halts. What you do? You restart the system. It is something like that. Abort all deadlock processes. Or you go for aborting one process at a time. Like you go for tax manager and delete one process. You go then another process, like that you do. So abort one process at a time. Abort the processes whose termination will incur so minimum cost. So I'll select a process which by terminating it will have minimum cost, means less resources it has taken. I'll try to abort it, or less work it has done, I can terminate it. Or in which order should we abort? We'll look into the priority, how long process has computed, resources, how many resources it has used, how much is required, how much extra time is required for terminating. So we'll consider these things before terminating the process. This is by process termination. The second one is by resource preemption. We can terminate the process, or we can also preempt the process. Okay. Okay. One more thing, that that in resource preemption, we will select a victim with the minimum cost and preempt it. Which resource has the minimum, which has hold the minimum resources, which will cost less, very less to us, we'll we'll preempt it. Or we'll roll back one by one. We'll roll back whatever the resources we have allocated. In the reverse order, we'll try to roll back one by one till the deadlock has breaked, till it has reached a safe state. Correct? And the starvation says that some processes may always be picked as victim. Suppose I choose a process as victim with the minimum cost. So the next time again a deadlock occur, and again I choose that. So every time it will be victimized. The same process may always be picked as victim. So include number of rollback in the cost per. So what we'll do, we have a fixed time, we'll have a fixed limit that how much time a particular process can be selected as a victim. Correct? Is it understood over here? Deadlock recovery can be done in two ways: process termination or by resource preemption. Process termination, what we'll do, we'll abort all processes, or we'll revoke one by one process, or we'll select a process with the minimum cost. And how to resource preemption? Resource preemption is we'll select a victim with minimum cost and preempt it, or we'll one by one will revoke the resources till a safe state is reached. We must ensure that a particular process, particular resource should not be selected always as a victim. Same process should not be selected always as a victim. Is that clear? Is it understood? This ends your third unit. The third unit is over today. See over here, the deadlock we have covered. Correct? So any doubt from here? It's almost time. It will end up because I have say less than 1 minute only. So if you have any doubt, the next class will discuss all those. So you ask me all those doubts. Along with that, we'll start with a new module, the memory management. If you have any doubt, you ask me now. Hello.
No doubt, sir.
Okay. You read it, and if it there in next class you ask, because today we have in a hurry of finishing all those. Next class, if you have doubt, you ask all those.